everybody. I'd like to welcome you to my talk about Java, of course, and about Java running in serverless, and about cold start and how fast Java is in serverless and also outside of serverless, just for a comparison, what it means and what are the implications of running Java in serverless environments like AWS Lambda, and also running outside of it, so that you see what is the overhead or what is the difference between them. So first, something about me. I've been in the Java community for a while, so I earned, for some reason, I don't know why, I earned the Java champion title, which doesn't mean so much, but it means I'm active in the community, and also I'm a Java user group lead in Czech Republic, and I'm active in several Jakarta EE specifications. And recently I co-founded a company called Omnifish, which is related to Glassfish and some other Jakarta EE projects and consultancies. Let's start with what actually is AWS Lambda and what it means to run serverless functions, especially in AWS Lambda, but most of the cloud providers have something similar. And when they invoke your application, your function, they need to first initialize the environment to run the cloud function. The reason is that cloud functions are designed so that they don't run always, they only run when they need to be executed. So you pay only for the execution time and not for all the time you have the application deployed. But for that, every time the application is not running, or there needs to be another instance of the application to be started to handle a higher load, a new environment, new sandbox for this application needs to be created first. And this is this phase when the new environment is created is called init phase. This is called also a cold start, because it only happens when the function is not warm. It means it wasn't run for some time, for a long time, and there's no active environment for it. So the environment has to be started, and the Java program has to be started. On the other hand, if the function is executed again on an active environment, the cloud provider can skip this first phase, because it's like the environment is cached. It remains there active for a while. If it's needed, it will be reused. If it's not needed for some time, it will be discarded. And after it's not needed, because the requests are not executed for some time, this invoke phase can repeat a lot of times for every request. But if it doesn't happen for some time, the cloud environment can shut down the whole environment, the whole sandbox for our function. And this is called a shutdown phase. No one knows when it happens. You don't read it in the documentation, you can only try. Usually it's after 10 to 15 minutes for AWS. For other cloud providers, it can be different. But you can expect it's minutes, it's not hours. It won't stay inactive for hours. And you only pay for the execution, actually, for the invocation of your function. But we can also modify what happens in the init phase, at least to some extent. You can see this red and blue part of the initialization phase is out of our control. This is handled by the cloud provider. The cloud provider sets up the runtime, injects some extension points to connect other services, like for logging, to capture the standard output into a logging service and things like that. And then it calls our Java application. We still don't have a control in the runtimes provided by AWS. We don't have control how the Java program is executed, but we can add some code to this initialization phase. And the question is how. In AWS Lambda, it's in static blocks, static methods. Everything that happens only once is run in this initialization phase. So you can put some code in static blocks, but there's also a limit. AWS will limit the time it takes to execute this code to very short time. I think it's 5 or 10 seconds at most. So we can do some initialization, but it can't take very long. And the catch is, or why is that? It's because we don't pay for this time. We don't pay for this execution. If we use the built-in AWS runtimes, AWS sets up the environment for us for free. It's paid by us for the resources, for the execution time, and also the code that initializes our application that runs in these Java static blocks is for free because it happens in the initialization phase. The only thing we pay is the actual method invocation, the actual business code that should process requests or multiple requests, so we pay for it, and that's most of the time. But we, when there is a cold start, we can run some code to initialize things, and it's not counted into our bill. But that's for supported runtimes in AWS. And what is a supported runtime? It's a runtime for every language that AWS supports. They provide a runtime. For some languages, they provide multiple runtimes based on the versions. For Java, for example, it's for version 8, version 11, and recently they also added support for Java 17, which is pretty nice because Java 17 has been already here for a while, but AWS didn't support it in the supported runtimes. But now it supports it, and you can just use it and deploy your code on Java 17 runtime. Before, if you want to customize your runtime, or before, if you wanted to use Java 17, you would have to create your custom runtime. And this is possible with AWS Lambda, but you have to provide basically everything on top of the operating system. You can modify the version of Java, installation of Java, you can install Java 17, even add some initialization scripts before the JVM is running. But the catch is you also pay for the execution, and not only of your code, but also on the mechanism that AWS runs. So that is there is a trade-off. Either you use the custom runtime and you have the advantage that if you add some static code to your application, it will be paid by AWS. But if you create a custom runtime, you have to pay also for the things that AWS uses or needs to do to prepare the runtime. But this is just a comparison. Now we have Java 17 runtimes in AWS, so unless we need to use some special JDK, or maybe we want to try Java 21 when it's out, we can use these built-in runtimes and we don't have to worry about anything else. Now, the question is that many people asked before, and I think that they still have doubts about it, is how fast Java is and how fast it is in AWS Lambda, because we heard stories that Java is very slow and Node and JavaScript are much faster, or Go is much faster. Nowadays Python is very popular and it's very fast to start. The problem is that not so many people measure how long it takes to finish the Lambda. And we don't have any numbers here about that, but the expectation is that Java is optimized. So if it runs, if the serverless function runs for a couple of seconds or even minutes, it will be faster to finish than the other languages, because it's compiled, and the compiler even compiles the application while it's running, so it improves the execution time in the time. While most of the other runtimes are either interpreted or they compiled up front and they never improve. But even if we look at Java startup times, we can see this is a comparison that somebody did. Like they measured a lot of times, many different runtimes on AWS, and they focus only on cold starts. The trick is you have to wait until the functions are cold, so they are not used, or you have to execute multiple of them in parallel, so every new one is a cold start. But with these measurements, these measures only cold starts of different runtimes and how long it takes to start a very simple application without any overhead of any framework or any application. And in the result, you can see that Java compares very well with the other languages. It's not significantly worse than the fastest runtimes, where the fastest is Python, JavaScript is, and Go is more or less the same. Java is just a little bit slower, but it's negligible because it's all just milliseconds, or up to half a second, so hundreds of milliseconds. And the truth is, if you switch to JavaScript or Go, you don't get much advantage in startup time. The problem is, if you start using frameworks, which most of us do if we run a Java application or if you write Java applications, then it gets worse. Because plain Java starts very fast, but frameworks take some time to initialize because they were not designed. A lot of them were not designed to start fast, but they were designed to provide a lot of features and initialize them up front, and then the application runs optimized because it's running for a long time. I just want to show you, just as a proof, how fast can Java be in a local computer. I have a simple application here. I don't know if you're interested in the source code, but I can show you quickly. Many of us don't write these applications nowadays. Only when we start learning Java, we do this. We print something from the main method and return. And that's the reason why we sometimes forget that Java can be really fast, because we deploy applications on application servers or use a framework, and then it takes some time to start. But with this application, if I run it and measure how long it starts, we'll see. I will run it like this. I have a simple script to measure the time until it starts and prints the message, and it's 67 milliseconds. So on my local computer, it's even much faster than in the cloud. And the reason is what I explained before. The cloud needs to initialize the environment first, and then it starts the application. And there's also another truth, that the CPU and the system on the cloud is slower actually than on my laptop, because it's usually 1 or 2 CPU cores, couple of gigabytes of memory at most. If you want to get more, you can get more, but you have to request, send the request to AWS. They will assign you more resources, but then you obviously pay for more. But this is the reason why my computer is faster than AWS Lambda. Not only because it creates the environment, but also because the CPU is slower. Now I want to record this in a graph here. I will just record this time, and later we will see how it compares. Now it's hard to compare, there's nothing. But when we have more numbers, I want to show you now a very similar application. Maybe something that you are more used to is to run it on a Glassfish server, a full-fledged Java EE server. This time is not a system out application, but it's a servlet. Very minimalistic solution for Java EE, which does very similar thing. But what it does more is it goes through the HTTP stack. So it calls, it turns an HTTP request on an HTTP listener to a server request. Then it converts server response to HTTP response. So it's not only logging into the output, but also exposing this through HTTP protocol, and you can call this through a browser. So let's compare quickly how fast it runs. Again, I have a script to start it and measure not only startup time of the server, but also the time until it's ready to serve the first request. So the script will actually issue a first request and then measure how long it takes to get the first response. So in this case, it's more than 5 seconds. And we can see that the application is running. It does this. So in the browser, we can see the output, similar what we saw in the plain application in the console. Let's record it here. Now we have a long time for Glassfish and almost negligible for Java because it's so small it's not visible in this graph. So the rest of my talk will be trying to answer this question. How can Jakarta EE be fast, as fast or close to that fast as a plain Java application server? And even like is this even possible? So yeah, the answer is yes, we can get very close to these plain Java startup times, just around 200, 300 milliseconds. In real life, we will get more to 1 second because we will need more components of the frameworks or of the solutions that we will show. But if we just use servlet and we need a servlet container and that's it, we can get very fast. First, I will introduce you to Quarkus framework. You probably already know about Quarkus framework, so I won't go too much into detail. There are many sessions, even on this conference, about Quarkus. But just to have it as a comparison to other solutions, I will introduce it and explain how it works under the hood, especially in the AWS Lambda environment. So Quarkus framework is basically a component-based framework. It has different components or so-called plugins that you can assemble together. And there are a lot of plugins for Jakarta EE functionality, for microprofile APIs, then also for some reactive APIs using Vertex. What is special about Quarkus? Quarkus does a lot of things at build time, so it parses your code, your configuration, and creates some bytecode and some optimizations that happen at build time, so they don't have to happen when you start the application. They are already prepared and the application starts faster than if these optimizations were happening in the beginning of starting your application. So that's at the core, and the CDI, the dependency injection of Quarkus, the Arc implementation uses this, and it generates a lot of stuff during build time, so it doesn't have to parse the annotations and create objects at runtime and create proxies at runtime. It creates a bytecode that is more optimized than proxies during runtime. Quarkus has a lot of plugins that also supports these ahead of time compilation or optimization at build time. So for many other libraries, they have some optimizations that can happen at build time, and they don't have to happen at runtime. It's built to be reactive at the bottom, and then you can write imperative code as you are used to, but you can always use the lower level reactive APIs. If you do it the other way, it's not possible to create reactive APIs on top of blocking APIs. So they did it this way. The core is a reactive, highly optimized engine. And then on top of it, you can have imperative blocking APIs because they are much simpler to use. So if you want to use them, you can. And also another important thing about Quarkus, it supports natively compilation to to native binaries using GraalVM. And that's possible because these plugins, they should have some support, or they should support GraalVM compilation. That's why it's good to use plugins and not directly libraries as dependencies, because these plugins are like a wrapper around popular libraries. And if you have already an existing plugin for a library, it can inject some important stuff for GraalVM, so that it can compile this library to a native image or native binary. Because some libraries out there use reflection, and this has to be somehow accounted for. So the plugin which wraps this library will provide all the information to compile it natively. So to show something in action, only some code. I won't run the application because it's very simple. Maybe just I will measure the same application that we had. So for an example how the application can be fast with Quarkus, I will basically do the same. I also have I lost my script. Oh, here it is. Okay, so I'll do again the same, just for comparison. The application again contains just a simple servlet, so it's as simple as it gets with Quarkus. The thing is that Quarkus still loads some things that I don't need, but it's not easy to turn them off. But it's again a Quarkus servlet. And when we run it with our measurement script, we can see we can get under 1 second, but not much faster. Maybe there are some optimizations in Quarkus, but on my computer with a very simplistic demo, when I edit a servlet, I got to 890 milliseconds, which is quite good, actually, if we compare it to application server. And also, if we compare it to Spring Boot, we can also compare Spring Boot application, which is very similar. I chose again to use servlets with Spring Boot, although with Spring Boot you would use probably something else than servlets. In fact, most of the time you wouldn't use servlets. You would use something like a REST API or some message-driven API. But servlet is the most simple common denominator that is supported by all these frameworks. So if I run the Spring Boot app, is the same thing. Just to show you the numbers, if you're interested. I need to stop the other one. Where is it? Oh. So now we have 1.7 seconds. Not bad, but Quarkus is faster. I have to remove the S from here. So now it's starting to get some shape. We can see that Glassfish is the slowest, which is understandable. Application servers were not designed to start fast. Yes, the question? Okay, I see. Thanks. So yeah, now we see something, but we see. Yeah, I wondered why it's not displayed. Well, it's very small. So if we remove Glassfish, just to get better comparison, Quarkus is around the half of Spring Boot, but plain Java is still like 10 times faster than Quarkus. And yeah, now I can also like explain how Quarkus works and what it does when we run run it in AWS Lambda, because it really does some interesting stuff, a lot of optimizations. But the trick, at least for me, the trick is or the catch is not easy to understand what's under the hood. So if it works well, then it's very good. If it doesn't work so well, it's hard to understand what's wrong and how to fix it. When we built the where is it? Oh, I think I lost it because I cleaned it up. Okay, so when we built the Quarkus application, Well, it builds a lot of artifacts. Some of them are things that should be deployed to AWS Lambda. Some of them are just helper scripts. And there is one artifact called runner, which you could use to execute the application, but the catch is it won't add the HTTP listener. So the application will be running, but there's no way to access the servlet inside it. You have to run the application in a different way to attach also the HTTP listener so that you can send the request and the request will be translated to the servlet. But this is a jar that we could run, and inside of this I'll extract it so we'll see what's inside. What is interesting that in our application, in the Quarkus application, we only have 2 classes. Oh, not this one. This Quarkus application. This is a more complicated application. It's a REST application. It contains, or it's a Lambda application. So it contains Lambda handler and some object that is injected to it. So it's already supports injection and some more things. But what it does, you can see, if I could make it bigger, there are only these 2 classes in the application. But in the result, after the compilation, you can see that in the package there are 2 for each. So there are 4 together. And there is always something dash bean and dash bean person dash bean and greeting lambda dash bean. Do you know why this is or what happened? These are the build time optimizations. This is basically what normally application server would execute or generate on the runtime. When you deploy the application, it will scan the annotations, it will create the proxies to inject dependencies. But Quarkus generates this code at build time. So at build, or when you run it, it already contains codes to create proxies in the bytecode, not generated code. It doesn't have to generate a new class type. It's already there in the bytecode. And everything, it just executes the code. So it's like a factory method. It calls the factory method defined in this generated class, and it will create a proxy and the dependency, and it will be able to inject it. And it doesn't have to have injection because this class runs in the same package, so it can basically just set the field if it's not completely private. So these type of injections are possible, these types of optimizations are possible if you do something at build time. Then you can offload something that would have to run at runtime. You can prepare some part of it at build time and then just run it at runtime, and it's faster. So that's about Quarkus. Now another framework that tries to address these the Java startup times, and also like general coding, improving Jakarta EE applications, let's say, it's Piranha Cloud. Piranha Cloud is a framework that is based around a completely new servlet container written from scratch, optimized to run fast and start fast and be easy to use, not dependent on anything else. So it's just a servlet engine. It doesn't even depend on HTTP. So you can execute it within your application and get some servlet response, and then just do something with the HTML probably or JavaScript that it generates. And it's also based on many components in Glassfish, which were extracted from Glassfish or already were a separate project of Glassfish, and it rebuilds the runtime based on these components. So it's like extracting everything from Glassfish and rebuilding things again, but this time not as a monolithic application server, but a highly flexible runtime, so that you can pick components you want, and these components integrate together as they find each other in the runtime. There are with Piranha Cloud there are no class paths, or actually There are possible ways, there are multiple possible ways to run the application, either to separate the runtime class path with your application's class path, but you can also merge them together and just embed the servlet engine inside your application, no class path magic. But it's also possible to run multiple Piranha Cloud instances in the same JVM if you want to run them completely isolated, and it has support for this and isolates the class path so that applications don't see each other classes. It contains several Jakarta EE distributions, which means that those are runtimes that contain Piranha Cloud and several components, and can be run as you normally run JVM with Java command and add a jar to it. This makes it possible to run the distribution and add your application, a web application WAR file or even ER file to it and deploy, so that you can separate the runtime and your application if you want. But it's also possible to merge them together and have just one single jar file that you can execute. And in the end, it's just plain Java. It's based on optimizations, based on simplicity. There's no magic. Maybe some magic would be beneficial to improve the startup times, but currently the focus in this project is to optimize the code and really just pick the components that are needed. Nothing, no boilerplate, nothing that's not needed. And this is how it compares to Quarkus. Quarkus tries to give you a lot and optimize the startup time by build time optimizations. So now some demo about Piranha, what it does and how it looks like. First, to impress you, I will run the same servlet with Piranha, and then I will explain how it works. Where do I have the Piranha function, Piranha up. So here again is a simpler servlet as we had before, but now since we add the runtime to the servlet together into our application, we don't deploy the servlet to an application server, and we have nothing in the framework to generate anything for us like Quarkus. We have to write some code to run the application, and there are two ways I prepared. One is to run a standard application with HTTP listener. For that, we need to create the Piranha engine. So we just initialize it, we set up the servlet and add it to the context path, to the root context path. Nothing really special, but we have to instruct it to find the servlet, because it doesn't have any magic to detect classes, detect annotations in the application. We can add an extension to do that, but that slows down the startup. So with this way, there's no class path scanning needed. It directly has access to the servlet. Then we start Piranha, and what we also need to do, as I said, it's just a servlet engine. We need to add some HTTP processor to connect the HTTP request, to create an HTTP listener and connect it to the servlet. Otherwise, we wouldn't be able to issue requests and actually call the engine. We could only call the engine from inside of our application, but not from outside. So if you want to call that outside from a browser, for example, we need to attach an HTTP processor. There is one default one, and there are, I think, multiple ones even for Project Loom and virtual threads. So you can choose, you can write one for yourself. And we create the HTTP server with this processor attached to the Piranha engine. And then we just start the HTTP server. So it goes in two stages. First, we initialize the servlet engine, and then the HTTP listener. It's useful, especially in AWS Lambda. I will come to that in a bit. So when we compare how fast it starts, shut down this one. It starts in 200 milliseconds. So if we compare it, we get a much faster startup time. And that's not it. We can even make it faster with the other alternative. If we don't start the HTTP stack, if we only start the engine. It doesn't really make sense in a microservice application where we need to expose some service through HTTP, but it makes sense in AWS Lambda, where the HTTP stack is provided by the cloud. And the AWS Lambda actually only executes a method in our code. So we don't need to create an HTTP listener. We just need a method that will process some request and create a response. And this is exact match for this case, where we don't create an HTTP listener. We only need the engine. And in order to simulate the execution of this engine, we only create a Piranha. We need to create some mock request and response. And then we print out the result of the response as string. So this is very similar to our plain Java application that also doesn't start an HTTP listener, but we already use the servlet engine and we invoke the servlet itself. So if we start this, we get almost to 100 milliseconds. Is that impressive or not? It's a very simple application, I know, but still it's possible to get very close. So now if we compare plain Java and Piranha Cloud with a very minimalistic application, we get almost the same times. And it's already Jakarta EE. It's only servlet, I know, but it's already something of Jakarta EE, and we can start it very fast. In reality, if we start a REST application, I have an example here. It takes almost the time that Quarkus takes to start. I need to shut down everything here so that it doesn't collide. But yeah, I wanted to say the truth that this is just a demo. It's real application or more realistic application, because the REST part of Piranha Cloud is not so optimized. We get to 900 milliseconds. But you see the possibility. It's possible to get very fast, and in the future when Piranha Cloud optimizes also the other parts of the stack, right, like REST stack, it can get faster. And you see that sometimes any magic is not needed, or build time compilation is not needed if the code is optimized to start itself fast. But always the build time compilation can make it better, but it's not the only way. One way is to improve the code itself and the framework itself. So now the final part is to show how this runs in AWS Lambda. And for that I have another example. The nice thing with Piranha is that you can have the same project and execute it on command line, and also in AWS Lambda, because you can just add a main method in your code and execute it, but you can also implement an AWS Lambda interface and run it. So here I have an example of an AWS function, Lambda function, that uses Lambda. And in AWS Lambda you can implement multiple interfaces. This one is to support REST requests or API gateway proxy requests, which means that API gateway is the HTTP listener in the cloud that creates an event for every request and sends it to our Lambda. And to respond to that, we have a method, and this method handler request is called in the invoke phase. So only this method is called for every incoming request. Everything else was called in the init phase or is never called. And you can see this is a static block which gets executed when the Piranha function class is loaded into the JVM, and this happens in the init phase. So the engine itself, everything is started in the initialization phase when the environment is created, and it doesn't have to be started for every request. It's prepared for with the first request, and then for every other request is already there. This is important because if we edit creation of the Piranha engine in the handler request method, it will be created for every request, and then it would slow down every request. With this solution, it only slows down the first request, the cold startup, but every other request will be fast. So just to demonstrate this, I will just execute the function. And hopefully we will see this cold start. Yes, this is a cold start. You can see a cold start from the response. I can't make it bigger. Here you see init duration on the right side. I'll try to make it bigger, but I can't scroll. Okay, I'll copy it so that you can see it. Hopefully there you can see it. There's init duration 500 milliseconds. This means that preparing the environment took half a second, and then there is build duration and duration, which is 40 milliseconds, which means the first time our Lambda is executed, it takes half a second to prepare the environment, prepare everything, and then it takes 40 milliseconds to start. And also, first start of the method takes usually a bit longer than subsequent method executions. So if we run it again, I will run it in this terminal. Now it's much faster, and there's no init duration, and there's only duration, which is 2 milliseconds, 1.72 milliseconds. So this means that every subsequent request takes just less than 2 milliseconds to process and to produce the response. So this is how it can get fast with complete cold start with Piranha Cloud. It's around 500 milliseconds. I'm using the maximum CPU that I can without asking AWS. So this also improves the startup time. But if you want to improve the startup times, in reality, it's like probably the most efficient and most easy way is to request more resources, more CPU to start your application faster. And sometimes even in the end you will pay less because you also pay for the execution time. And if you have more resources for your Lambda function, it will finish faster. So in the end, the total cost may be more or less the same, and you get faster startup times. So to finish my presentation, so I already said, if you want further optimize execution or startup, you can increase the resources, but you can also choose a faster JVM or optimize the JVM options. I did some very simplistic tests with 2 JVMs. I think it was Corretto on my local computer, because Corretto is also used by AWS in each of the services. And I tried Java 11, Java 17 with simple service. I think this was based on Quarkus. And you can see that most of the time you can get the same startup times, but very often in Java 17 you get better startup times with some options. And when you compare this one, expired stop at level C2 disabled, you get much better times than the others. So normally you get around 800 milliseconds. With this you get 700 milliseconds. So that's quite a big optimization. And the truth is, by default, AWS sets it already for the provided Java runtime. So you don't need to worry about this. This option is already set. So it speeds up the startup time of Java applications by default. And another option would be to use CDS, which is so-called class data sharing, so that you preload the classes the first time you execute your application, then you record all the metadata about classes, and the next time you start your application with this metadata, it can skip this phase of gathering metadata about classes, and it's a bit faster. But in the end, you don't need to use class data sharing, because there is already a newer and better approach, which is CRAC, continuous or restoration. Some restoration and checkpoint. I don't remember the whole name. And this is a new project in OpenJDK, which you could use outside of AWS Lambda. But in AWS Lambda, you can use so-called AWS SnapStart, which is a technology inside AWS Lambda, which is basically based on this project. And what both of them do is they are able to take a snapshot of a running application, hibernate it to disk, and then next time you start it with this hibernated data, it will restore your application to the exact same point. So it's like hibernation of your computer. It will hibernate your environment in the AWS Lambda, and all subsequent calls are faster. And AWS SnapStart does it while you deploy the application. So when you deploy the application, it will take some time until it gets compiled or prepared, and then every subsequent start will just restore the environment and will not recreate it every time and again and again. And this is nice because as AWS recently added support for Java 17 runtime as a built-in runtime, it also supports a SnapStart with this. If you create your own custom runtime, you don't have this out of the box. You would have to use a Java virtual machine that supports this CRAC itself, and it's a lot more work than just use SnapStart. Actually, SnapStart is just some configuration on your service so that it creates a so-called version of the service, and when you call that version, it automatically triggers SnapStart, and your startup time is much faster. I would like to show it, but I don't have much time to do it, so if you're interested after the talk or later, I can show you how this works. I think that's basically all what I wanted to say, and I already mentioned GraalVM compilation, so this is another way. Only it's technically possible with Piranha Cloud, but Piranha Cloud doesn't have any specific support for GraalVM, so you may hit some problems with Quarkus. Quarkus supports it natively, so if you use only plugins in Quarkus, it should work out of the box. But the downside is that with native binary, there are other challenges that you don't have with JVM, so there is always a trade-off. In conclusion, I wanted to show you, and I hope I impressed you at least a bit, that Java is not slow. It's frameworks that are slow, and Java can be very fast. And if you choose the right frameworks and you need your Java to start up fast, then you have options. You can use either Piranha or Quarkus to start your applications very fast and have a lot of options to optimize them even further. And what is nice about Piranha and Quarkus is that a lot of their APIs are very similar. They are based on Jakarta EE. Quarkus also adds some microprofile APIs which are more or less standard, which Piranha hopefully will implement in the future too. But the general feeling is the same. If you know these APIs, you will be familiar with both frameworks. They just have different approaches. Quarkus uses ahead of time compilations, build time optimizations, while Piranha tries to optimize the actual initialization of the framework at runtime. So that's it. I don't know if you have any more questions. Let me know, or feel free to come here and talk to me after the talk. I have a few T-shirts. If you'd like to have some T-shirts like I have here, I'm happy to share with you. And here are some links. And thank you for your attention.